A thin film of lubricant is the only thing preventing metal-to-metal contact between the many moving parts in your facility's equipment. If the lubrication fails, expensive machinery can be destroyed in seconds. One of the most widely used types of lubricating devices is a hand-operated grease gun. Many grease guns can be filled directly from a drum through a fitting. These are called bulk load grease guns because they are filled directly from a bulk supply of grease. Grease is pumped into the gun with a device called a grease gun filler. The filler is often simply a hand pump that is installed on a grease drum. The outlet of the hand pump is attached to the fitting on the grease gun and the handle is pumped. When you start to feel resistance to pumping, the gun is full. The cap should always be replaced. Other types of grease guns are filled by replacing cartridges. The top of the gun is unscrewed, and then on this gun, a plunger at the end is pulled back and used to push the empty cartridge out. The plunger is pulled back and locked in position to make room for the new cartridge. This new cartridge is opened by removing a plastic bottom cap and a metal pop top. It's placed in the gun barrel bottom first, and the top is screwed back on. To finish up, the plunger is released and shoved all the way in. Once a gun is filled, it's used to pump grease through a fitting into a machine part. Most of the time, that will be a bearing in a housing. Before lubricating a bearing, it's always a good idea to check it to see if it's running hot. The simplest way to do that is to feel the housing. You may want to try it with a glove on first. If it doesn't feel hot, you can check it with your bare hand. A hot housing is a sign there's too much friction, possibly because there isn't enough lubricant or the wrong lubricant was used. A hot running bearing should be reported for maintenance. Many bearing housings have a drain hole to let old grease out. The plug in the drain hole is unscrewed before new grease is added. It's important to use a clean rag to wipe off the grease fitting so dirt won't be pumped in. The tip of the gun is placed over the fitting and grease is pumped in. On a bearing with a drain plug, the gun should be pumped until the old grease is forced out. In most cases, the new grease will be a slightly different color, so watching for a color change is one way to tell that the old grease has been forced out. Sometimes, however, the old grease mixes with the new and it's hard to tell them apart. In that case, you may have to estimate when the old grease has been forced out by the amount that's come out. After adding grease, the drain hole is wiped off and the plug screwed back in. If the bearing isn't turning during greasing, plant procedures may require the machinery to be turned on for a few minutes before putting the plug back in. That distributes the grease in the bearing and forces out any excess. Many facilities have pneumatic or air-powered grease guns. This air-powered dispenser consists of a pump that fits on a grease drum. An air hose connected to a source of compressed air supplies air to power the pump. The pump moves grease from the drum through a hose to a grease gun connected to the end of the hose. A trigger on the gun is operated to release grease. Be sure to check your plant procedures when you're greasing a bearing. They may tell you how much grease to apply and whether the equipment needs to be running or not. Some bearings are lubricated automatically. This large sleeve bearing, for example, has no seals. Grease oozes out between the bearing and the shaft. On this bearing, the lost grease is replaced from a reservoir or cup. The cup slowly but continually feeds grease to the shaft through a hole in the bearing. A spring-loaded disc forces grease out of the cup and into the bearing. Containers such as this one should be checked periodically to make sure they're not running low on grease. If the level in this cup is low, it's refilled using a grease gun. Some grease cups are operated by hand. Grease is forced into a bearing by turning the top of the cup. Devices used to inject grease into bearings can be quite a bit more complicated than simple grease cups. These centralized lubricators, for example, contain hydraulic pumps that automatically supply lubricant to heavy machinery. The one on the right pumps oil, and the one on the left pumps grease. This is a simplified illustration of the grease system. This is the cylinder that contains the grease supply. The motor and pump that force grease out to the bearings are at the base of the cylinder. A single line supplies grease to several bearing housings. There are two main things to check on this type of lubricator: lubricant level and lubricant pressure. On this unit, a level indicator shows how much grease is in the cylinder. A pressure gauge is installed in the grease line. If a blockage stops grease flow, pressure in the line will cause the gauge to read well above normal pressure. If the pump fails or the system runs out of grease, the gauge will read low. The first step in lubricating a piece of equipment is to obtain the right lubricant. Moving parts can fail just as quickly from the wrong kind of lubricant as they can from a contaminated lubricant or from no lubricant. Once you've determined the right lubricant to use on a particular piece of equipment, you need to get it from storage. So next, we'll look at two ways that oil can be obtained from the containers that it's stored in. Oil used in industry is often stored in large drums. One way to get oil out of these large drums is with a spigot. One type of spigot is opened by pushing down on the handle, which is spring-loaded. The handle closes itself when it's released, although it's a good idea to pull it tight so it won't leak. We've just seen a spring-loaded spigot, but there are other types of spigots commonly used in industry. Some spigots have a valve that is turned to dispense oil. Oil can also be drawn out through the top of a large drum with a hand pump. This hand pump has a drip collector that's pulled aside. The oil can is held under the spout. On this model, the handle is first turned one way to prime the pump, then turned back to pump oil into the can. When the can is pulled away, this drip collector automatically swings into position under the spout. We've seen how to select the right lubricant for the job. We've also seen a couple of ways to dispense oil from large drums. In this part, we'll discuss some oil lubricating devices. We'll look at a drip feed oiler, some oil baths, and a ring oiler. Let's start with the drip feed oiler. A drip feed oiler is an automatic lubricating device used in industry for many different applications. In this example, drip feed oilers are being used to lubricate a chain drive. There are two oilers, one for each side of the chain. Glass reservoirs hold the oil supplies. As this illustration shows, oil drips from each reservoir into pipes hanging over the chain. A sight glass at the bottom of each reservoir can be checked to see if oil is dripping through at the correct rate. Most facilities have guidelines that specify what the correct drip rate should be. On this oiler, the drip rate is adjusted by turning a knob at the top of the reservoir. A lever above the knob is used to shut the oil flow off entirely. That's usually done when the device being lubricated is shut down. The oil level can be checked by looking through the glass reservoir. If it's low, the reservoir should be refilled. Oil is added through a small opening at the top. The lid should be clean so that no dirt falls in when it's opened. Another method of lubrication, the oil bath, allows components to be partially immersed in a supply of oil. Oil baths provide oil for lubrication and also for cooling. In this example, a gear sits in a supply of oil. As the gear turns, its teeth pick up oil and carry it with them. The oil is transferred to other gears as they mesh with the one in the oil bath. Oil baths are also good for lubricating rolling element bearings. The balls or rollers pass through the supply of oil and carry the oil with them as they rotate. There's an easy way to check the oil level in many bearing housings and gear casings. This sight glass indicates the level of oil in a casing containing gears driven by an electric motor. The oil level in oil baths is usually different depending on whether the equipment is running or not. So when checking oil levels in your facility, be sure you know whether it should be checked with the equipment on or with it off. The level in some oil reservoirs can't be checked when the equipment is running. That's because the oil is churned around so much that it's impossible to determine an accurate reading. In this large gearbox, for example, the oil level is checked with a dipstick. With the unit off, the dipstick is wiped off. Then it's pushed all the way back down into the oil and pulled out again. The level is above the low mark, so it's in the acceptable range. If it were at or below the low mark, more oil should be added. When checking the oil level in any reservoir, it's also a good idea to check the oil's condition. If the oil has turned dark or feels gritty, it may be contaminated by dirt or products of oxidation. If water has contaminated the oil, it can acquire a milky appearance. It may be necessary to identify the source of the contamination before replacing the oil. The oil baths we've seen so far all use a gear casing or bearing housing as a reservoir for oil. But there are other types of oil baths that have reservoirs outside the housing. This one, for example, has a glass reservoir that automatically releases more oil into the bearing housing when it's needed. The open end of the reservoir sits in a cup, which is connected to the bearing housing by a pipe. As this illustration shows, the level of oil in the cup is the same as the level in the housing. The bearings are lubricated as they spin through the oil in the housing. When a small amount of oil leaks out of the housing, oil automatically flows from the bottle to keep the oil in the housing at a constant level. So this system is known as a constant level oiler. Another name for it is a bottle oiler. The bottle reservoir should be nearly full. This one needs refilling. To fill a bottle oiler, turn it upside down and pour in new oil until it's full. Then put it back in the cup. The main thing to check a bottle oiler for is a faster than normal drop in oil level. If that happens, there may be a leak somewhere that should be fixed as soon as possible. Oil baths work well with gears and ball or roller bearings. Now let's look at sleeve bearings. Most sleeve bearings need a way to get oil in between the journal and the bearing. One way of delivering oil to a horizontal sleeve bearing is with a ring oiler. From the top, the oil ring is just visible under the oil filler cap. It's a bronze ring that rides on the journal. On this partially disassembled ring-oiled bearing, you can see how the oil ring fits in a gap in the sleeve bearing. The ring is large enough to hang down into a reservoir of oil in the bearing housing. As the journal rotates, the ring turns with it. The rotating ring brings oil up to the top of the journal from the reservoir in the bottom of the housing. There's an inspection opening at the top of the housing. The opening is used to observe the movement of the ring. The ring should turn smoothly. If it isn't turning at all, the bearing won't be lubricated. The opening is also used for adding oil to the reservoir. The oil level is checked through a flip cup on the side. The oil level in this unit should be halfway up the cup. In some lubrication applications, gravity or the rotation of equipment can't supply enough oil. In these cases, a circulating oil system driven by a pump is used. This piece of equipment contains a heavy shaft that spins at very high speed. Each end of the spinning shaft is supported by a roller bearing in a housing. Each bearing is lubricated by a system that circulates oil through it. Let's look at a simplified illustration of this system to see how it works. Here is the shaft, and here are the bearings. The pump for this circulating oil system sits on a tank called a sump. The sump holds the oil supply. An electric motor drives the pump. The pump draws oil out of the sump and sends it to a filter. The filter removes dirt and metal particles worn from the bearings. A gauge indicates the pressure of the oil. The oil then passes through a cooler. From the cooler, the oil flows to a T, where the flow splits to go to each of the bearings. A flow indicator in each line shows the flow rate to the bearings. Oil enters the bearing housings, lubricating the bearings. The return lines carry the oil back to the sump. Your duties on a system such as this will probably include checking oil pressure, flow rate, and oil level. In this system, oil level is checked with a dipstick located under the sump's filler cap. You should also check for leaks in oil lines and bearing seals. For large systems, you may have a panel with gauges that indicate oil pressure and temperature. There may also be alarms that indicate system malfunctions and low oil levels. Most bearings are enclosed in housings. In addition to supporting and protecting the bearing, the housing also serves as a reservoir to hold the supply of oil or grease that lubricates the bearing. With most bearings, the opening where the shaft leaves the housing is sealed to keep lubricant from escaping and contaminants from getting in. Probably the simplest type of seal is a contact seal. It's usually made of a relatively soft material, such as felt, synthetic rubber, cork, or a synthetic material such as silicone. This model shows how the inner rim of a contact seal fits on a shaft. This illustration shows how the outer rim of a contact seal fits tightly in a bearing housing to keep lubricant from escaping. The inner rim, or lip, presses against the spinning shaft. A seal in good condition will allow only a very small amount of lubricant to seep between the lip and the shaft. The lubricant reduces friction between the seal and the shaft. The lip on a contact seal will eventually wear down, however, allowing lubricant to leak out at an unacceptable rate. For this reason, checking lubricant seals may be an important part of your duties. Any seal allowing a noticeable amount of lubricant to escape should be reported. Contact seals used with grease can be damaged by over-lubrication. Excess grease will be forced out under the lip. This can deform the seal and allow even more grease to leak out. If too much grease leaks out, the bearing could fail. So lubricate bearings with contact seals carefully according to your plant procedures. Another type of seal is a labyrinth seal. A labyrinth seal consists of two sets of interlocking metal ridges. In this particular design, one set of ridges is attached or built in to the bearing housing. The other set is part of a ring that fits tightly on the shaft. As this illustration shows, the narrow gap between the ridges is like a maze or a labyrinth. That's why this type of seal is called a labyrinth seal. Both the twisting path created by the ridges and the small clearance between the ridges restrict flow. While both labyrinth seals and contact seals are used to help restrict the flow of lubricants, they can't be relied upon for all fluids and in situations where it's necessary to virtually eliminate fluid flow. For example, when hazardous fluid is contained in a housing, even a small amount of leakage would be undesirable. To minimize fluid leaks in these situations, another type of seal called a mechanical seal is often used. This illustration shows a cutaway of a mechanical seal. A typical mechanical seal consists of a rotating element which mounts to the shaft and presses against a stationary element which mounts to the housing. Each element has a seal ring. This side view shows a cross-section of the two rings. They form a seal that has virtually no leak-off. To prevent the seal rings from being damaged, some type of lubricant must be supplied to them. In some applications, the process liquid is used as the lubricant. In other applications, an external liquid may be used to lubricate the seal rings. The external liquid is sometimes referred to as a seal flush. Here is a line that supplies external fluid to a mechanical seal. To keep process fluid from leaking out along valve stems, the stems of many valves are sealed with packing. Valve packing is frequently a rope-like material soaked with a lubricant such as oil, grease, or powdered graphite. The lubricant reduces friction between the packing and the valve stem. The packing fits snugly around the valve stem. The motion of the valve stem can gradually wipe away some of the lubricant where the stem contacts the packing. If that happens, the valve may start to stick. To keep that from happening, this valve has a fitting that allows grease to be pumped between the packing and the valve stem. After wiping the fitting to prevent contamination, the worker uses a grease gun to apply grease. Your facility procedures may specify how much and what kind of grease to apply. After the grease gun is removed, excess grease is wiped off the fitting. This prevents dirt and other contaminants from sticking in the grease and collecting around the fitting. Another method for applying grease to the valve stem is with a lubricator. To apply the grease, the bolt on this lubricator is screwed in until the grease in the lubricator is pushing against the valve stem. In this topic, we discussed how seals restrict leakage and how valve packing can be lubricated. Take some time now to try a couple of practice questions.